Right now, ancient light is racing toward your eyes from the farthest reaches of existence. Some of these photons began their journey 13.8 billion years ago, before Earth existed, before our Sun ignited, before the Milky Way took its current shape. They carry information from a time when the universe was a screaming infant of superheated plasma. But here is what will shatter everything you thought you knew about cosmic boundaries. There is no wall out there, no edge you could crash into, no barrier marking where reality ends. The edge of the observable universe is not a place at all. It is a horizon created by time itself, a limit on what we can ever know, receding forever beyond our grasp. If you want to understand what truly exists at the boundary of everything we can see, hit that like button and subscribe. It truly means the world to me. Now, get yourself comfortable. Let's begin. The fastest thing in the universe is not a spacecraft. It is not a particle accelerated in a laboratory. It is not even the explosion of a dying star. The fastest thing in existence is light itself, racing through the vacuum of space at 186,282 miles per second. At this velocity, a photon could circle Earth 7.5 times before you finish listening to this sentence. Light crosses the distance from the moon to your eyes in just 1.3 seconds. It travels from the sun to Earth in 8 minutes and 20 seconds. This cosmic speed limit represents the absolute maximum velocity at which any information, any signal, any physical influence can propagate through the fabric of reality. Einstein proved this over a century ago. Nothing carrying mass or information can exceed light speed. This is not merely a technological limitation we might someday overcome. It is woven into the fundamental structure of space-time itself. Push a particle closer to light speed, and it requires increasingly infinite energy. Reach light speed, and time itself stops from the perspective of the traveler. Exceed it, and causality breaks down, with effects preceding causes in paradoxes that physics does not permit. The speed of light is not just fast. It is the cosmic speed limit enforced by the deepest laws of nature. Yet here is what makes this speed limit so consequential for understanding the edge of the observable universe. Despite being incomprehensibly fast by human standards, light is agonizingly slow across cosmic distances. The nearest star system to our Sun, Alpha Centauri, sits 4.24 light-years away. Light leaving that stellar neighbor tonight will not reach Earth until the year 2030. The center of our Milky Way galaxy lies 26,000 light-years distant. Photons, beginning their journey from those crowded stellar regions, will arrive at Earth 26,000 years from now, long after every human alive today has turned to dust. Scale this up further. The Andromeda Galaxy, our nearest major galactic neighbor, floats 2.5 million light-years from Earth. The light you see from Andromeda tonight left that galaxy when early human ancestors were first learning to chip stones into primitive tools. 2.5 million years of travel time at the fastest possible speed in the universe, and Andromeda counts as remarkably close in cosmic terms. Most galaxies we observe lie billions of light-years away. Their light has been travelling toward us for spans of time that dwarf the entire existence of complex life on Earth. This is where the concept of the observable universe begins to take shape. We exist inside a bubble defined not by walls or barriers, but by time itself. The universe is approximately 13.8 billion years old. Scientists have confirmed this age through multiple independent methods, including measurements of the cosmic microwave background radiation, observations of the oldest stars, and calculations based on the expansion rate of space. 13.8 billion years represents the total elapsed time since the Big Bang, the moment when our universe began its existence in a state of unimaginable density and temperature. Now combine these two facts. Light travels at a finite speed. The universe has existed for a finite time. The inevitable conclusion reshapes everything we think we know about cosmic boundaries. We can only observe objects whose light has had sufficient time to reach us since the universe began. Any object, so distant that its light would require more than 13.8 billion years to arrive, remains forever invisible. Not because something blocks our view, not because our telescopes lack power, but because the photons have not had enough time to make the journey. They are still travelling through space right now, racing toward us at the cosmic speed limit, but they have not arrived yet. Some never will. The edge of the observable universe is not a place. It is a moment in time. Specifically, it is the moment beyond which light has not had sufficient duration to reach our position in space. This edge exists at the same distance in every direction we look, creating a sphere of visibility centered on Earth. But this sphere does not mark where the universe ends. It marks where our ability to observe ends. The distinction is critical and frequently misunderstood. The observable universe has an edge. The universe itself may not. Consider an analogy that captures this distinction without creating false impressions of physical barriers. Imagine standing on a ship in the middle of the ocean. You can see the horizon in every direction, a circle surrounding you where the curvature of Earth blocks your view of more distant waters. That horizon is not the edge of the ocean. Vast expanses of water extend far beyond what you can see. The horizon represents the limit of your observation from your particular vantage point, not the limit of what exists. If you sailed toward the horizon, you would never reach it. It would recede ahead of you continuously, always the same distance away, because the horizon is defined by your position and the geometry of observation, not by any physical feature of the ocean itself. The edge of the observable universe works similarly, but with a crucial difference. Instead of spatial geometry creating the horizon, temporal constraints create it. The age of the universe combined with the speed of light determines how far we can see. And unlike the ocean horizon, which you could theoretically approach by sailing, the cosmic horizon cannot be reached through any conceivable travel. Moving toward it does not bring it closer. Traveling at light speed would not help you catch up to it. The edge is not somewhere you can go because it is not fundamentally a place. It is a temporal boundary projected onto the spatial structure of the cosmos. Every observer in the universe sits at the center of their own observable sphere. This statement sounds disturbingly Earth-centric, reminiscent of ancient beliefs that our planet occupied a privileged cosmic position. But the physics here carries no implication of specialness. Alien astronomers in a galaxy 3 billion light-years from Earth would have their own observable universe centered on their location. Their sphere would overlap substantially with ours, sharing many of the same visible galaxies, but it would also extend into regions we can never see while excluding regions visible to us. Every point in space defines its own observational horizon. There are as many observable universes as there are potential observers, all different, all equally valid, none occupying a privileged position. The observable universe spans a diameter of approximately 93 billion light-years. This number creates immediate confusion for anyone paying attention to the earlier discussion. If the universe is only 13.8 billion years old, how can we see objects 93 billion light-years away? Should not the maximum distance be limited to 13.8 billion light-years in any direction? This paradox dissolves once we account for cosmic expansion, a phenomenon we will explore in depth shortly. For now, understand that space itself has been stretching throughout cosmic history. Objects that emitted light toward us billions of years ago have since been carried to much greater distances by the expansion of the universe. When we observe the most ancient light, we see it as it was emitted from regions that were much closer back then. Those same regions now lie far beyond the simple light travel time calculation would suggest. But what exactly do we see when we look toward the edge of the observable universe? What exists at the farthest reaches of human visibility? The answer is both beautiful and frustrating. We see the past. The distant universe is not merely far away in space, it is far away in time. Every observation of a distant object is simultaneously an observation of ancient history. Look at the sun, and you see it as it appeared 8 minutes ago. Look at the Andromeda galaxy, and you see it as it appeared 2.5 million years ago. Look at the most distant galaxies detectable by the James Webb Space Telescope, and you observe them as they existed over 13 billion years ago, when the universe was less than 5% of its current age. These infant galaxies appear small, chaotic, and violently active because they genuinely were small, chaotic, and violently active at that ancient epoch. We are not seeing these galaxies as they currently exist. We are seeing their baby pictures, frozen light carrying information about conditions that ceased to exist eons before Earth formed. This temporal displacement intensifies as we push our observations toward the observable edge. The farthest electromagnetic radiation we can detect is not the light of ancient galaxies. It is something far more fundamental. It is the afterglow of the Big Bang itself, a faint radiation that fills all of space and reaches us from every direction. Scientists call this the cosmic microwave background radiation, and it represents the oldest light in the universe, the oldest thing we can possibly see using electromagnetic radiation of any kind. The cosmic microwave background was released approximately 380,000 years after the Big Bang. Before this moment, the universe existed in a state that prevented light from traveling freely. The entire cosmos was filled with a superheated plasma, a seething fog of free electrons and atomic nuclei so dense and energetic that photons could not travel any meaningful distance without colliding with charged particles. Light was trapped, scattered endlessly, unable to stream across space. The universe was opaque, glowing with temperatures that had cooled from billions of degrees in the earliest moments to roughly 3,000 degrees at the moment of recombination, but revealing nothing of distant regions, because visibility through this cosmic fog extended only microscopic distances. Then temperatures dropped below a critical threshold. Electrons slowed enough to be captured by atomic nuclei, forming the first stable atoms of hydrogen and helium. This process, called recombination, transformed the universe in an instant. With free electrons suddenly locked inside neutral atoms, photons found themselves able to travel unimpeded. Light was released. The cosmic fog cleared. The universe became transparent for the first time in its existence. The radiation released during recombination has been traveling through space ever since. Those ancient photons have journeyed for 13.8 billion years, and they continue arriving at Earth from every direction today. We detect them as a faint microwave glow filling the entire sky, a background hiss of radiation with a temperature of just 2.725 degrees above absolute zero. This chilling temperature results from the extreme stretching these photons have experienced during their immense journey. Cosmic expansion has lengthened their wavelengths by a factor of over 1,000, draining their energy from the visible and infrared spectrum down into the microwave range. When scientists map this cosmic microwave background radiation with sensitive instruments, they are producing the most distant image possible with light. They are photographing the universe as it appeared 380,000 years after the beginning, when atoms first formed and transparency began. This radiation comes from what cosmologists call the surface of last scattering, the spherical shell surrounding us, from which those ancient photons began their journey toward our detectors. Beyond this surface, we cannot see using any form of electromagnetic radiation, not because nothing exists there, but because the universe was opaque earlier, and any light from those epochs was absorbed and re-emitted countless times before the cosmos cleared. The cosmic microwave background therefore marks a fundamental limit on electromagnetic observation. It is not a wall or barrier in any physical sense. You could not travel to it, touch it, or crash into it. The surface of last scattering is a when, not a where. It represents a moment in cosmic history visible from our position because sufficient time has elapsed for that ancient light to reach us. The photons arriving from the cosmic microwave background have travelled farther than any other light we detect, and the regions that emitted them now lie approximately 46 billion light-years away due to cosmic expansion during the journey time. This creates a profound realization about the nature of cosmic observation. We do not see the universe as it exists now. We see it as it existed at various points in its past, with the most distant observations revealing the most ancient eras. Our telescopes are time machines, not in the science fiction sense of travelling to different epochs, but in the very real sense of collecting information from periods long vanished. The photons entering a telescope today carry data about conditions that ceased to exist billions of years before our solar system coalesced from interstellar gas. The edge of the observable universe is therefore not a boundary in space so much as a boundary in time. When we speak of the observable edge, we speak of the limit beyond which light has not had sufficient duration to reach us. This edge extends outward in every direction at the same distance, creating a sphere centered on Earth with a radius of approximately 46.5 billion light-years. Everything within this sphere can potentially be observed. Everything beyond it remains hidden, at least for now. But what actually lies beyond the cosmic microwave background? What existed before recombination in those opaque early moments we cannot directly observe with light? Scientists possess substantial knowledge about these hidden epochs despite their invisibility. The physics of the early universe leaves signatures in the patterns we do observe, allowing researchers to work backward from visible evidence to reconstruct conditions in the cosmic fog. Before recombination, the universe was smaller, hotter, and denser. Every point in space was closer to every other point. The cosmic soup of plasma that prevented light from traveling freely was nearly uniform in density, but not perfectly so. Tiny variations in density existed, quantum fluctuations amplified to macroscopic scales during an extremely brief period of explosive expansion called inflation. These density fluctuations represented regions with slightly more matter and regions with slightly less. The fluctuations were minuscule, variations of only about 1 part in 100,000 from perfect uniformity, but they were enough. These density variations left imprints on the cosmic microwave background radiation. Regions with slightly higher density appear slightly warmer in cosmic microwave background maps. Regions with slightly lower density appear slightly cooler. The pattern of hot and cold spots encodes information about conditions before recombination, before the universe became transparent, before light could travel freely. Scientists analyze these patterns to reconstruct the physics of epochs they cannot directly observe, inferring conditions in the hidden era from signatures preserved in the oldest visible light. The temperature variations in the cosmic microwave background also seeded the formation of all cosmic structure that followed. Those slight density enhancements became gravitational wells that attracted surrounding matter over billions of years. They grew into the first stars, the first galaxies, the vast cosmic web of filaments and voids that defines large-scale structure today. Everything we observe in the modern universe traces its origin to those tiny fluctuations imprinted on the cosmic microwave background. This connection between the oldest observable light and the subsequent evolution of cosmic structure reveals something profound about the edge of the observable universe. The edge is not merely a limit on what we can see. It is a window into the initial conditions that determined everything that followed. By studying the cosmic microwave background, we glimpse the universe at its most primitive observable state, the starting point from which all complexity emerged through billions of years of gravitational evolution. But even the cosmic microwave background is not the ultimate edge. It is merely the electromagnetic edge, the limit of what light can reveal. Other forms of observation might eventually penetrate deeper. Neutrinos, ghostly particles that interact only weakly with matter, decoupled from the cosmic plasma about 1 second after the Big Bang, far earlier than photons did. A cosmic neutrino background exists, analogous to the cosmic microwave background but from a much earlier epoch. Detecting these ancient neutrinos remains beyond current technology, but future instruments might achieve it, pushing our observational horizon back to within the first second of cosmic existence. Gravitational waves offer another potential window into epochs before recombination. These ripples in space-time travel at light speed and interact with matter even less than neutrinos do. Gravitational waves from the primordial universe, if they exist with detectable strength, could carry information from the inflationary epoch or even earlier, revealing conditions less than a trillionth of a second after the Big Bang. Detecting such waves represents a monumental technological challenge, but nothing in physics prohibits it. The edge of the observable universe is therefore not fixed or final. It represents the current limit of our observational reach, determined by the types of signals we can detect and the duration those signals have had to travel. Improvements in detection technology can push the edge backward in time, revealing earlier cosmic epochs, but certain fundamental limits remain. We can never observe anything from before the universe began, whatever that phrase might mean. We can never observe anything that requires more travel time than the age of the cosmos to reach us. The edge may shift, but some version of it will always exist. Understanding the observable edge requires abandoning intuitions developed on Earth. Human experience provides no preparation for thinking about cosmic horizons. We are accustomed to edges that mark physical boundaries, walls, cliffs, shorelines. The edge of the observable universe shares none of these properties. It is not a surface you could touch. It is not a barrier blocking passage. It is not even a single definable location in space, since it depends entirely on the observer's position and the elapsed cosmic time. The edge is better understood as the place where time runs out, where the finite age of the universe catches up with the finite speed of light and says, no further. No more photons have had time to arrive from greater distances. Whatever exists beyond remains hidden not by any obstacle, but by the simple mathematics of duration and velocity. Distance equals rate multiplied by time. When time is finite, the observable distance has a maximum value. This maximum defines our cosmic prison. We are confined to a bubble of visibility not by walls, but by the relentless tyranny of light speed and cosmic youth. Every photon that reaches us has been travelling for some portion of 13.8 billion years. The oldest photons carry information from the most distant sources. The most distant sources lie at the edge of our observable sphere. Beyond that edge, the universe continues, but we cannot see it. We cannot detect it. We cannot know with certainty what exists there. Yet the nature of this prison is stranger still. The edge is not static. It shifts and changes in ways that seem paradoxical, until you account for the expansion of space itself. Our observable universe grows larger with each passing moment as light from increasingly distant regions arrives for the first time. Tomorrow we will observe slightly more cosmos than today. Next year, slightly more still. This growth would seem to suggest that eventually we might observe everything, that given sufficient time, the edge would retreat until the entire universe lay within our visible sphere. But this optimistic conclusion fails to account for a discovery that transformed cosmology in 1998. The expansion of the universe is not slowing down. It is speeding up. Dark energy, a mysterious component comprising roughly 68% of cosmic contents, drives acceleration that works against our expanding view. Galaxies at extreme distances recede from us faster than light itself, due to the expansion of space between us and them. This recession carries them beyond our future observational reach, even as light from their current positions streams toward us. The observable universe is growing larger, but also becoming increasingly isolated from regions that will never be observable no matter how long we wait. The edge expands outward, but an event horizon of cosmic isolation expands faster. We are gaining access to new reaches of the visible cosmos while simultaneously being cut off from an ever larger portion of the universe beyond. This tension between revelation and concealment defines the edge of the observable universe. It is a boundary of knowledge, not of existence, a limit imposed by physics, not by the structure of reality. And as we will discover, this boundary behaves in ways that challenge every assumption we might hold about cosmic edges and what they reveal about the nature of existence itself. The expansion of space creates the edge. The acceleration of expansion shapes its fate. To understand what happens at the edge, we must first understand why space itself is stretching, and what happens when that stretching exceeds the cosmic speed limit. In 1929, an astronomer working at Mount Wilson Observatory in California made a discovery that shattered humanity's understanding of the cosmos. Edwin Hubble had been measuring the distances to spiral nebulae, fuzzy patches of light that astronomers had debated for decades. Were these objects clouds of gas within our Milky Way, or were they entire galaxies lying far beyond our stellar neighbourhood? Hubble's distance measurements settled the question decisively. These nebulae were galaxies in their own right, vast collections of billions of stars located millions of light years from Earth. The universe was suddenly far larger than anyone had imagined, but Hubble noticed something even more startling in his data. When he combined his distance measurements with observations of the light these galaxies emitted, a pattern emerged that made no sense under existing assumptions about cosmic structure. The light from distant galaxies was systematically shifted toward redder wavelengths. More distant galaxies showed greater redshift. The relationship was remarkably consistent. Double the distance and you double the redshift. Triple the distance and the redshift triples proportionally. Something fundamental was affecting light from distant sources, and that something grew stronger with increasing distance. The explanation for this redshift transformed cosmology from a study of static cosmic geography into the science of cosmic evolution. Those distant galaxies were not simply sitting at fixed positions in space. They were moving away from us. The redshift Hubble observed resulted from the Doppler effect, the same phenomenon that causes an ambulance siren to drop in pitch as it speeds away from you. Light from receding objects gets stretched to longer wavelengths, shifting toward the red end of the spectrum. The greater the recession velocity, the more pronounced the redshift. Hubble's observations implied something remarkable about cosmic motion. Every distant galaxy was receding from Earth. Not just some galaxies in particular directions, but all of them, in every direction astronomers looked. Furthermore, the recession velocities increased with distance, in a precise linear relationship now called Hubble's law. Galaxies twice as far away recede twice as fast. Galaxies 10 times farther recede 10 times faster. This pattern held across the entire observable cosmos. The natural first interpretation might suggest that Earth occupies some special central position from which all galaxies flee, but this geocentric conclusion fails completely under closer examination. The same pattern would appear to observers in any galaxy throughout the universe. An astronomer in the Andromeda galaxy would see Earth receding. An observer in a galaxy 3 billion light-years away would see both Earth and Andromeda receding from their position. Everyone sees everything else moving away, and the recession velocity increases with distance regardless of where you stand. This universal recession pattern has only one coherent explanation. Space itself is expanding. The galaxies are not racing through a static void like fragments from an explosion scattering through empty space. Instead, the fabric of space-time is stretching, carrying galaxies along with it like raisins in rising bread dough. The raisins themselves do not move through the dough. They sit fixed in the mixture, but as the dough expands, every raisin sees every other raisin moving away. Raisins farther apart separate faster, because more dough lies between them, and all that intermediate dough is stretching simultaneously. This distinction between motion through space and expansion of space proves critical for understanding the edge of the observable universe. Objects moving through space obey Einstein's cosmic speed limit. Nothing can travel faster than light through the fabric of space-time. But space itself faces no such constraint. The expansion of the universe is not motion in the conventional sense. It is the creation of new space between objects, the stretching of distances without anything actually travelling anywhere. This stretching can occur at any rate, including rates that exceed light speed when measured across sufficiently large distances. The mathematics here are precise and confirmed by decades of observation. Hubble's law states that recession velocity equals a constant multiplied by distance. This constant, called the Hubble constant, measures approximately 70 kilometers per second per megaparsec. A megaparsec equals roughly 3.26 million light-years. So a galaxy 1 megaparsec away recedes at 70 kilometers per second. A galaxy 10 megaparsecs away recedes at 700 kilometers per second. A galaxy 100 megaparsecs away recedes at 7,000 kilometers per second. Follow this relationship to its logical extreme. At some distance, the recession velocity reaches the speed of light. Calculate this distance using the Hubble constant, and you get approximately 14 billion light-years. This distance defines the Hubble radius, a sphere surrounding every observer beyond which recession velocities exceed light speed. Galaxies beyond the Hubble radius are being carried away from us by the expansion of space faster than light could travel from them to us through that same expanding space. This might seem to create an obvious boundary to the observable universe. If galaxies beyond 14 billion light-years recede faster than light, surely no signal from them can ever reach us. The logic appears airtight. Light cannot outrun the expansion carrying its source away, so we should be forever blind to anything beyond the Hubble radius. But this intuition, though reasonable, turns out to be completely wrong. We observe galaxies far beyond the Hubble radius regularly. The most distant galaxies detected by the James Webb Space Telescope lie over 30 billion light-years away in terms of their current distance. Light from these galaxies reaches our instruments despite their superluminal recession. This apparent paradox dissolves once we think carefully about what happens during a photon's journey across expanding space. Consider a photon emitted from a distant galaxy long ago, when the universe was much younger and smaller. At the moment of emission, that galaxy was much closer to our location than it is today. Perhaps it lay only 3 billion light-years away. The light began travelling toward us at the cosmic speed limit, aiming to cross that 3 billion light-year gap. But during the journey, space kept expanding. The distance between the photon and Earth kept changing, sometimes growing faster than the photon could close it, sometimes slower. In the early universe, expansion rates were higher in some senses, but the universe was so much smaller that light from distant sources could make progress toward us. The photon might find itself temporarily losing ground as expansion outpaced its travel, but conditions change over cosmic time. Expansion rates vary depending on what dominates cosmic energy content. For billions of years, the photon gradually gains ground, crossing expanding space faster than new space forms ahead of it. Eventually it enters regions where recession velocities drop below light speed, the space closer to Earth where expansion is gentler. From there, arrival becomes inevitable. Meanwhile, the galaxy that emitted the photon has been carried to ever greater distances by continuous expansion. By the time the ancient light finally reaches our telescopes, its source has receded to 30 or 40 billion light-years away. We see the galaxy as it was billions of years ago, when it was much closer. We cannot see it as it exists today, and we never will because light leaving that galaxy now will never reach us. The expansion has carried it beyond our future observational reach, even though its ancient light still arrives from journeys begun in a younger, smaller cosmos. This creates a subtle distinction between different types of cosmic horizons. The Hubble radius marks where current recession velocity equals light speed. This is not the edge of the observable universe because light from beyond this distance, emitted long ago, can still reach us. The particle horizon marks the true edge of the currently observable universe, the maximum distance from which light has had time to reach us since the Big Bang. This lies farther out, approximately 46 billion light-years, because it accounts for the entire history of expansion and light travel rather than just current conditions. But there is a third horizon more troubling than either of these. The cosmological event horizon marks the distance beyond which light emitted right now will never reach us in the entire future of the universe. This horizon exists because expansion is not merely ongoing but accelerating. Dark energy drives the universe to expand faster and faster over time. Regions beyond the event horizon will recede faster than light can ever cross the intervening space, no matter how long we wait. The event horizon represents a fundamental limit not just on current observation, but on all possible future observation. The discovery that cosmic expansion is accelerating came as a shock to the scientific community. Throughout the 20th century, astronomers assumed that gravity would gradually slow the expansion over time. Galaxies pull on each other across cosmic distances. This mutual gravitational attraction should act as a brake, decelerating the expansion initiated by the Big Bang. Researchers debated whether this deceleration would eventually halt and reverse the expansion, causing a big crunch, or merely slow it asymptotically toward a steady coasting state. Nobody seriously considered that expansion might actually be speeding up. In 1998, two independent research teams studying distant Type Ia supernovae discovered that the universe had other plans. Type Ia supernovae serve as cosmic distance indicators because they all explode with nearly identical brightness. By measuring how bright a supernova appears from Earth and comparing this to its known intrinsic luminosity, astronomers calculate its distance. The observed brightness tells you how far the light traveled. The redshift tells you how much space expanded during the journey. Combining these measurements reveals the expansion history of the cosmos. Both research teams expected to find evidence of decelerating expansion. Instead, they found the opposite. Distant supernovae appeared fainter than predicted, meaning they were farther away than expected. The expansion of space had carried their host galaxies to greater distances than a decelerating universe would allow. The data demanded an accelerating cosmos, one where expansion speeds up over time rather than slowing down. This discovery earned the 2011 Nobel Prize in Physics and revolutionized our understanding of cosmic composition. Something was pushing space apart, overwhelming gravity's tendency to pull things together. Scientists name this mysterious influence dark energy, a label acknowledging that we know what it does while remaining largely ignorant of what it actually is. Dark energy comprises approximately 68% of the total energy content of the universe, making it the dominant component of cosmic reality. Yet its fundamental nature remains one of the greatest unsolved problems in physics. The leading theoretical candidate for dark energy is the cosmological constant, a term Einstein originally introduced into his equations of general relativity and later abandoned. The cosmological constant represents energy inherent to empty space itself, a property of the vacuum that exerts negative pressure, pushing space to expand against gravitational attraction. If dark energy is indeed a cosmological constant, its density remains fixed as the universe expands. This constancy has profound implications. As space expands, matter and radiation become diluted. Double the volume of space and you halve the density of matter within it. The gravitational influence of matter, therefore, weakens over cosmic time as expansion spreads it thinner. But if dark energy maintains constant density, its total amount increases as new space forms. Dark energy does not dilute, it accumulates. Given enough time, dark energy inevitably dominates over matter and radiation, and accelerating expansion becomes unavoidable. The transition to dark energy domination occurred approximately 5 billion years ago. Before this epoch, matter density was high enough that gravitational attraction slowed the expansion, though not enough to reverse it. After the transition, dark energy took control. Expansion began accelerating and has continued speeding up ever since. This acceleration shapes everything about the observable edge of our universe and what happens there. Consider what acceleration means for the cosmic horizon. In a universe with decelerating or constant expansion, we would gradually observe ever more distant regions as light from them finally completed its journey to Earth. The observable universe would grow continuously larger, with no fundamental limit other than the particle horizon set by the age of the cosmos. Given enough time, we might eventually see essentially everything that exists, as light from all reaches of space eventually completed the trek to our detectors. Accelerating expansion destroys this possibility. As expansion speeds up, the event horizon moves closer. Regions that we could theoretically observe, given infinite time, become permanently inaccessible, as the expansion rate increases faster than light can compensate. The cosmic horizon is not merely the current limit of observation. It is becoming an eternal prison wall, enclosing us within a shrinking fraction of total cosmic reality even as our visible sphere continues growing. This seems contradictory but results from the different behaviors of different horizons. The particle horizon, marking what we can currently see, expands outward as ancient light continues arriving from distant sources. We observe more of the cosmos with each passing moment, but the event horizon, marking what we can ever see, contracts inward as acceleration intensifies. We gain access to ancient history while losing access to contemporary reality in distant regions. The rate of this isolation is not measured in human timescales but in cosmic ones. Over the next several billion years, galaxies currently visible near the edge of our observable universe will fade from detectability as their light redshifts beyond instrumental sensitivity. Over tens of billions of years, the acceleration will carry nearly all external galaxies beyond the event horizon. In the extremely distant future, perhaps 100 billion years from now, observers in our region of space will find themselves within a cosmos containing only the merged remnants of our local group of galaxies. Everything else will have been carried beyond all possible observation. Future astronomers living in that isolated era will face a universe that appears radically different from the one we see today. They will observe their local galactic structure, perhaps a giant elliptical galaxy formed from the merger of the Milky Way and Andromeda, surrounded by apparent emptiness. The cosmic microwave background radiation will have redshifted beyond detection. Distant galaxies will have vanished beyond the event horizon. Evidence of the Big Bang, of cosmic expansion, of the rich galactic populations we observe today, will have been erased from the observable record. These future astronomers, if they exist, might reasonably conclude that the universe consists only of their isolated galaxy floating in static, empty space. The expansion history of the cosmos will leave no detectable signature within their limited horizon. The Big Bang model that we consider well established today will be unsupportable by their observations. Cosmology as we know it will have become impossible, not because the universe changed its nature, but because accelerating expansion will have hidden the evidence. This scenario reveals something profound about the edge of the observable universe. The edge is not merely a current limitation that better technology or more time could overcome. For a wide class of observations, the edge represents a permanent, fundamental barrier enforced by the laws of physics. Accelerating expansion ensures that most of the universe lies forever beyond our reach, not just beyond current capabilities, but beyond all possible future observation regardless of technological advancement. The photons traveling toward us right now from the most distant visible galaxies represent the last light we will ever receive from those sources. Future photons emitted by those same galaxies will never complete the journey. They will race toward us through space that expands faster than they can cross. They will lose ground continuously, falling ever farther behind despite traveling at the cosmic speed limit. These photons will travel forever without ever arriving, condemned to eternal pursuit of a destination receding faster than light speed. Consider the strangeness of this situation. Light emitted today from a galaxy just beyond our event horizon will travel for infinite time without reaching us. It will cross countless light years of space. It will pass through the expanding void for billions upon billions of years, and it will never arrive, not because anything absorbs it, not because it runs out of energy, though redshift will drain it toward ever lower frequencies, but because the space ahead of it keeps growing faster than the photon can traverse it. The universe will expand forever, the photon will travel forever, and the gap between emission and detection will grow forever wider. This perpetual pursuit occurs throughout the cosmos. Countless photons are traveling toward observers they will never reach, carrying information that will never be received, bearing witness to events that will remain forever unknown. The edge of the observable universe is not a static boundary but an active process of cosmic censorship, constantly rendering new regions of reality permanently inaccessible. The expansion of space also transforms the light that does manage to reach us. Photons traveling through expanding space get stretched along with the space itself. This stretching increases wavelength and decreases frequency. Blue light shifts toward red light shifts toward infrared shifts toward microwave. The longer the journey through expanding space, the more the light gets stretched. This cosmological redshift differs subtly from the Doppler shift caused by motion through space. Though both produce reddened light from receding sources, Doppler shifts result from velocity of the source relative to the observer at the moment of emission or detection. Cosmological redshift results from the cumulative expansion of all the space traversed during the photon's journey. For distant sources, this cosmological stretching dominates, creating redshifts far larger than any velocity-based Doppler effect could produce. The most distant objects we observe show redshifts exceeding 10, meaning their light has been stretched to wavelengths more than 10 times longer than originally emitted. Ultraviolet light from these primordial sources arrives as infrared radiation after billions of years of cosmic stretching. The James Webb Space Telescope was specifically designed with infrared sensitivity to detect these extremely redshifted ancient sources, looking back to epochs when the first galaxies formed. But redshift does more than change colors. It drains energy from photons. A photon's energy is inversely proportional to its wavelength. Double the wavelength and you halve the energy. Stretch light by a factor of 10 and you reduce its energy to 1/10 the original value. The most ancient photons reaching us carry only tiny fractions of their original energy, weakened by billions of years of cosmic expansion. This energy loss has practical consequences for observation. Distant objects appear fainter, not just because their light spreads across larger areas with increasing distance, but also because each arriving photon carries less energy than when it left. Detecting the most distant sources requires instruments sensitive to extremely faint, highly redshifted signals. Even with the most advanced telescopes, there are limits to how dim and red a signal can become while remaining detectable. Some sources have faded beyond these limits while still technically lying within our observable universe. The expansion of space also affects time itself. From our perspective, events in distant galaxies appear to occur in slow motion. A supernova that takes weeks to brighten and fade in its host galaxy takes months or years when observed from Earth, stretched by the same cosmological expansion that redshifts its light. Time runs differently across cosmic distances, not because of any physical difference in the flow of time at those locations, but because the space carrying temporal information expands during transit. This time dilation provides another tool for measuring cosmic expansion history, but also complicates the interpretation of transient events at extreme distances. Understanding cosmic expansion reveals the dynamic nature of the observable edge. This boundary is not painted onto space like a line on a map. It emerges from the interplay between light speed, cosmic age, and the expansion history of the universe. Different expansion histories would create different boundaries. A universe expanding faster would have smaller observable volumes. A static universe would have an observable region limited only by cosmic age times light speed, without the complications of recession, velocity, and event horizons. Our actual universe, dominated by dark energy and accelerating, creates an observable edge that behaves in counterintuitive ways. The edge grows larger as we receive ancient light from distant sources. Simultaneously, the edge becomes more impenetrable as acceleration strengthens the barrier against future observation. We observe more of cosmic history while becoming permanently isolated from more of cosmic geography. The numbers involved challenge human comprehension. The current observable universe spans 93 billion light-years in diameter, containing approximately 2 trillion galaxies. Yet this represents a shrinking percentage of the total universe, assuming the total universe extends far beyond our observable portion. As expansion accelerates, we see a larger absolute volume, but a smaller fraction of cosmic totality. In the far future, our descendants might observe trillions of light-years of space while remaining isolated within an infinitesimally small bubble of an unimaginably larger cosmos. The edge of the observable universe therefore represents something more than a limit on current knowledge. It represents an evolving boundary between the knowable and the eternally unknowable. Regions that were once potentially observable have crossed beyond our event horizon and will never be seen. Regions currently visible will eventually follow them into cosmic darkness. The expansion of space continuously reshapes what we can observe, what we can never observe, and what we are in the process of losing forever. This dynamic edge raises profound questions about what exists beyond it. The universe presumably continues beyond our horizon, filled with galaxies, stars, and planets similar to those within our visible sphere. But we cannot confirm this assumption through direct observation. We cannot point telescopes at regions beyond the edge and see what is there. We cannot send probes to investigate those distant reaches. We are limited to inference, extrapolation, and theoretical reasoning about a cosmos that refuses to reveal itself completely. The expansion of space creates our observable bubble and simultaneously defines its limits. Every second, that bubble grows slightly larger as ancient light arrives from newly accessible distances. Every second, that bubble becomes more isolated as accelerating expansion strengthens the walls of our cosmic prison. We exist at a particular moment in cosmic history, neither too early to see distant galaxies, nor too late to observe the evidence of universal expansion. Future observers will not be so fortunate. What exists beyond the edge remains the central question. Cosmic expansion tells us that something exists there, that space continues beyond our horizon, that galaxies presumably populate those distant reaches just as they populate the space we can observe. But the edge prevents confirmation. It transforms certainty about our local cosmic environment into inference about regions we can describe mathematically but never observe directly. The expansion that reveals so much about cosmic structure simultaneously conceals most of cosmic reality behind an ever-strengthening veil of accelerating space. Scientists operate under a remarkable assumption when studying the cosmos. They assume that the laws of physics observed here on Earth apply everywhere throughout the universe and at all times throughout cosmic history. This assumption, called the uniformity of nature, cannot be proven from first principles. It represents a foundational premise that makes scientific cosmology possible. Without it, every observation would apply only to its specific location and moment, rendering universal conclusions impossible. This assumption has proven spectacularly successful within the observable universe. The same gravitational constant that governs falling apples on Earth determines the orbits of distant binary stars. The same electromagnetic force that powers our light bulbs creates the spectra of galaxies billions of light years away. The same nuclear physics that drives our sun fuels stellar furnaces across the entire visible cosmos. Everywhere astronomers have looked, the fundamental forces and constants of nature appear identical to those measured in terrestrial laboratories. The cosmic microwave background radiation provides particularly compelling evidence for this uniformity. This ancient light arrives from every direction in space with nearly identical temperature, varying by only a few hundred thousandths of a degree across the entire sky. Such uniformity suggests that the early universe was extraordinarily homogeneous, with the same physical processes occurring throughout the observable volume. The tiny temperature fluctuations that do exist follow patterns predicted by well-understood physics, further confirming that familiar laws operated even in the universe's infancy. This observational success within our cosmic bubble emboldens scientists to extend the uniformity assumption beyond the observable edge. If physics operates identically across 93 billion light-years of observable space, spanning 13.8 billion years of cosmic history, why should it suddenly change beyond our horizon? No theoretical framework suggests any reason for physics to differ in unobservable regions. No mechanism exists that would enforce different laws beyond the edge while maintaining identical laws within it. The simplest hypothesis holds that the universe continues operating under familiar principles regardless of whether we can observe any particular region. But this extrapolation, however reasonable, represents inference rather than observation. We have no direct evidence about conditions beyond the observable edge. We cannot send probes there. We cannot receive signals from there. We cannot conduct experiments whose results depend on what exists there. Everything we claim about the unobservable universe amounts to educated assumption, theoretical extrapolation, or mathematical inference. The distinction between what we know through observation and what we assume through reasoning becomes critical when discussing the edge of the observable universe. The cosmological principle formalizes this extrapolation into a testable framework. This principle asserts that the universe is homogeneous and isotropic on sufficiently large scales. Homogeneity means the same everywhere, no special locations, no privileged positions, no unique centers. Isotropy means the same in all directions, no preferred orientations, no cosmic up or down, no directional asymmetries. Combined, these properties describe a universe that looks essentially identical regardless of where you stand or which way you look, provided you average over large enough volumes to smooth out local irregularities. Within the observable universe, evidence strongly supports the cosmological principle. Galaxy surveys reveal that cosmic structure becomes increasingly uniform at larger scales. On scales of tens of millions of light years, galaxies cluster into groups and filaments separated by vast voids. On scales of hundreds of millions of light years, even this cosmic web structure averages out into statistical uniformity. No direction contains significantly more galaxies than any other. No region shows systematically different properties than any other region of comparable size. The cosmic microwave background provides even stronger evidence. This radiation arrives from shells of space surrounding us at the maximum observable distance, sampling conditions at the edge of our visible universe in every direction simultaneously. The extraordinary uniformity of this radiation demonstrates that the universe was homogeneous and isotropic at the time of recombination, 380,000 years after the Big Bang. Slight variations exist, but they represent fluctuations of only 1 part in 100,000 around perfect uniformity. Scientists use this observed uniformity within our cosmic bubble to justify assumptions about regions beyond it. If the observable universe is homogeneous and isotropic, the reasoning goes, then regions beyond our horizon should share these properties. The universe should continue with similar galaxy populations, similar cosmic structures, similar physical processes operating under similar fundamental laws. This assumption allows cosmologists to build models of the total universe based on observations of our limited sample volume. But the cosmological principle cannot be verified beyond the observable edge. It remains an assumption, albeit a well-motivated one, about regions we can never directly examine. Alternative possibilities exist, even if they seem less parsimonious. The universe might become fundamentally different beyond our horizon. Physical constants might vary in unobservable regions. The density of matter might change dramatically at some distant boundary. We cannot rule out these possibilities through any conceivable observation because no observation can reach beyond the cosmic horizon. The geometry of space provides another window into what might exist beyond our direct observation. Einstein's general relativity describes how mass and energy curve the fabric of spacetime. This curvature manifests as gravity on local scales, but also determines the global geometry of the universe. Space might be positively curved like the surface of a sphere, bending back on itself such that traveling far enough in any direction eventually returns you to your starting point. Space might be negatively curved like a saddle, stretching away from itself in all directions without limit. Or space might be flat, extending indefinitely without curvature, described by the familiar Euclidean geometry of high school mathematics. Observations strongly favor a flat universe. Measurements of the cosmic microwave background, combined with data on galaxy clustering and cosmic expansion, constrain spatial curvature to be extremely close to zero. If the universe has any curvature at all, it is so slight that we cannot detect it across our entire observable volume. This flatness has profound implications for what lies beyond the edge. A perfectly flat universe would extend infinitely in all directions. There would be no boundary, no edge to space itself, no point where the cosmos ends. Such a universe would contain infinitely many galaxies, infinitely many stars, infinitely many planets, extending forever beyond our horizon. Our observable bubble would represent an infinitesimally small fraction of infinite cosmic totality. Everything we can see, the 2 trillion galaxies, the hundreds of billions of stars in each galaxy, the countless planets orbiting those stars, would amount to precisely 0% of the actual universe. Even if the universe has slight positive curvature undetectable with current measurements, the total cosmos would vastly exceed our observable portion. Geometric calculations based on observational limits suggest that the total universe must be at least 250 times larger than the observable universe in linear extent. This means the total volume exceeds our visible volume by at least 15 million times. Some estimates based on inflationary cosmology suggest the total universe might exceed the observable universe by factors so large that writing them out would require more digits than atoms in our visible cosmic sphere. These calculations do not tell us what exists in those unseen regions. They merely establish that something exists there, that space continues far beyond our horizon, that the cosmos dwarfs our observable bubble by factors that resist human comprehension. The flatness of space provides evidence for extension beyond the visible, without providing any information about the contents of that extension. Inflationary cosmology offers a theoretical framework for understanding what might lie beyond our horizon, though this framework remains provisional and unconfirmed in many of its details. Inflation proposes that the very early universe underwent a brief period of exponential expansion, doubling in size many times over in a tiny fraction of a second. This rapid expansion stretched a microscopic region of primordial space to cosmic scales, smoothing out initial irregularities and establishing the homogeneity we observe today. If inflation occurred, it would have expanded the universe to sizes far exceeding our current observational reach. Different inflationary models predict different total sizes, but most suggest the cosmos extends vastly beyond what we can see. The observable universe would represent a tiny patch of a much larger post-inflationary volume, a patch so small relative to the whole that its edge would appear perfectly flat, even if the total universe has measurable curvature. Inflation also provides a mechanism for the uniformity we observe. Regions now separated by the entire diameter of the observable universe would have been in close contact before inflation began. They would have reached thermal equilibrium, sharing identical temperatures and densities before explosive expansion carried them to opposite sides of our cosmic horizon. The remarkable uniformity of the cosmic microwave background would reflect this pre-inflationary equilibration rather than any implausible coincidence. But inflation remains a theoretical framework rather than a confirmed fact. While many predictions of inflationary theory match observations, the mechanism itself has not been directly detected. The specific physics driving inflation remains unknown. The energy scales involved exceed anything achievable in terrestrial experiments. Alternative explanations for cosmic uniformity exist, even if they currently seem less compelling than inflation. Claims about the total size of the universe based on inflationary calculations must be understood as theoretical extrapolations, not observational facts. The edge of the observable universe, therefore, marks a boundary not just of visibility, but of epistemological certainty. Within our horizon, we possess genuine knowledge based on direct observation. We can photograph galaxies, measure their spectra, track their motions, and analyze their compositions. We can test theoretical predictions against empirical data. We can build increasingly accurate models constrained by ever more precise measurements. Science operates in its normal mode, refining understanding through observation and experiment. Beyond the horizon, we possess only inference. We can extrapolate current theories. We can assume the cosmological principle continues holding. We can calculate what inflation predicts if inflationary theory is correct, but we cannot check these inferences against observations. We cannot falsify incorrect assumptions through empirical testing. We cannot distinguish between models that make identical predictions within the observable volume, but differ in their claims about unobservable regions. This limitation is not technological. It does not result from insufficiently powerful telescopes or inadequate detection methods. The boundary between observation and inference at the cosmic edge is fundamental. built into the structure of space-time itself. No conceivable technology could overcome it, because the limitation results from the finite speed of light and the finite age of the universe, properties that constrain all possible observers, regardless of their capabilities. The edge of the observable universe cannot be reached through travel. This seems counterintuitive. Surely, if you flew toward the edge in a sufficiently fast spacecraft, you would eventually arrive there, pass through it, and enter the unobservable regions beyond. But this reasoning fails completely when applied to cosmic horizons. The observable edge is defined by the observer's position, not by any feature of space at any particular location. Travel toward the edge, and you carry your observable sphere with you. The center of your visible universe remains wherever you are. Objects that were near the edge before your journey remain near the edge after, though slightly different objects may populate that boundary. You never get closer to the edge because the edge is not somewhere. It is everywhere at the maximum distance from which light has had time to reach you. Imagine moving toward what you initially perceive as the edge of the observable universe. You accelerate to enormous speeds and travel for millions of years toward a distant galaxy that appeared near your original horizon. When you arrive at that galaxy, you can observe it directly. You have brought it within your immediate locality, but the edge of your observable universe still lies at the same distance it always did, roughly 46 billion light-years away. The edge has not moved closer. Your sphere of visibility has simply shifted to center on your new location while maintaining the same radius determined by cosmic age and light travel time. Furthermore, traveling toward the edge actually reduces what you can ultimately observe rather than increasing it. During your journey, the universe continues expanding. Time passes. Cosmic acceleration strengthens. Regions that were marginally within your future observational reach when you began the journey have crossed beyond the event horizon by the time you arrive at your destination. Your journey to approach the edge has cost you more observable universe than it gained, precisely because the edge is not a fixed boundary you can approach, but a dynamic horizon defined by your relationship to cosmic expansion and light travel. This feature of the cosmic edge distinguishes it fundamentally from the edges we encounter in everyday experience. The edge of a table is a specific location in space. Walk toward it and you get closer. Touch it and you have reached it. Pass it and you have gone beyond it. The edge of the observable universe shares none of these properties. It has no specific location. Movement toward it accomplishes nothing. You can neither touch it nor pass beyond it because there is nothing there to touch and no boundary to cross. The cosmic microwave background sometimes creates confusion on this point. Descriptions of this radiation as the oldest light in the universe, or the boundary of the observable universe, can suggest that it represents some kind of physical surface existing at a specific distance. This impression is fundamentally mistaken. The cosmic microwave background is not a wall. It is not a barrier. It is not even properly speaking a place. The radiation we detect as the cosmic microwave background was emitted throughout all of space at a specific time in cosmic history. 380,000 years after the Big Bang, recombination occurred everywhere simultaneously. Photons began traveling freely throughout the entire universe at that moment, heading in all directions from all locations. The radiation we detect today consists of those photons that happen to be emitted in our direction from locations now approximately 46 billion light-years away. From any position in the universe, an observer would detect essentially identical cosmic microwave background radiation arriving from their own horizon. They would see photons emitted during recombination from regions now at maximum observable distance from their location. Different observers at different cosmic positions see different photons from different source locations, but all see radiation with the same temperature, the same spectrum, the same statistical properties. The surface of last scattering surrounds every observer in the universe like a private sphere of ancient light. This radiation tells us about conditions during recombination throughout space, not about conditions at any particular location we could visit. The photons carry information about temperature, density, and composition at the moment they were released. They reveal the presence of tiny density fluctuations that seeded cosmic structure formation. They encode the proportions of ordinary matter, and dark energy that characterize the early universe. This information applies to the cosmos as a whole during that epoch, not to specific regions at the edge of our observable volume. The temperature fluctuations in the cosmic microwave background merit special attention. These variations, though tiny in absolute terms, appear as hot and cold spots scattered across the microwave sky. Their pattern is not random. It exhibits specific statistical properties that reveal fundamental aspects of cosmic physics. The size distribution of hot and cold spots, their correlations with each other, and their relationship to larger-scale patterns all encode information about the universe's composition, geometry, and early evolution. These fluctuations represent density variations in the primordial plasma at the moment of recombination. Regions slightly denser than average attracted more matter gravitationally, compressing and heating the plasma slightly, producing hotspots in the cosmic microwave background. Regions slightly less dense than average expanded and cooled slightly, producing cold spots. The pattern we observe today has been carried to us across cosmic time, preserving information about conditions when the universe was 1,000 times smaller and millions of times hotter than today. The density fluctuations revealed by the cosmic microwave background grew over billions of years into all the cosmic structure we observe. Hot spots in the ancient radiation correspond to regions that developed into galaxy clusters and cosmic web filaments. Cold spots correspond to regions that became cosmic voids. The seeds of structure visible in the cosmic microwave background blossomed through gravitational amplification into the 2 trillion galaxies that populate our observable universe. This connection between ancient radiation and modern structure confirms that physics operated consistently throughout cosmic history. The same gravitational processes that explain star formation and galaxy dynamics also explain how microscopic density fluctuations in the early universe grew into the largest structures in the cosmos. The uniformity of physical law across observable time complements its uniformity across observable space, strengthening the inference that similar laws operate beyond our horizon. But the cosmic microwave background also marks a hard limit on electromagnetic observation. Before recombination, the universe was opaque. Photons could not travel freely through the cosmic plasma. Any electromagnetic radiation from earlier epochs was absorbed and re-emitted countless times before the universe cleared, scrambling the information it might have carried. We cannot see what existed before the surface of last scattering using any form of light, from radio waves to gamma rays. The cosmic microwave background represents the first frame of the cosmic movie, visible to electromagnetic observers. This limitation does not mean earlier epochs are completely inaccessible. Other messengers might carry information from times before recombination. Neutrinos, nearly massless particles that interact only through the weak nuclear force, decoupled from the cosmic plasma about 1 second after the Big Bang. A cosmic neutrino background should fill space today, analogous to the cosmic microwave background but far more ancient. Detecting these primordial neutrinos would push our observational horizon back by hundreds of thousands of years, though current technology remains inadequate for this task. Gravitational waves offer another potential window into the pre-recombination universe. These ripples in space-time propagate at light speed and interact with matter so weakly that they can traverse the entire observable universe, essentially unimpeded. Gravitational waves generated during inflation, if they exist with sufficient strength, might still be detectable today. Their observation would provide direct evidence about conditions less than a trillionth of a trillionth of a trillionth of a second after the Big Bang, pushing our horizon back to the earliest conceivable moments of cosmic history. Neither cosmic neutrinos nor primordial gravitational waves have been detected yet. Their observation represents a major goal of current and future experiments. Success would dramatically extend our empirical reach into cosmic history, replacing theoretical inference with direct measurement for epochs currently beyond observation. But even these exotic messengers cannot overcome the fundamental limitation imposed by cosmic age. We cannot observe anything from before the universe existed, however we interpret that phrase. Some boundary to backward observation must exist. even if we can push it to ever earlier times. The limits of inference become most apparent when considering what the total universe might contain beyond our horizon. We can reasonably assume that galaxies similar to those we observe populate unobservable regions. We can expect stars, planets, gas clouds, black holes, and all the phenomena familiar from our cosmic neighborhood. The cosmological principle and the uniformity of physics support these assumptions, but we cannot verify them, and we must remain open to the possibility that our assumptions fail in ways we cannot anticipate. Consider a specific example of inferential limitation. Within the observable universe, we measure specific values for fundamental physical constants. The gravitational constant, the speed of light, the masses of elementary particles, the strengths of fundamental forces all take particular values we can determine experimentally. These values appear identical everywhere we have been able to measure them, but could they differ in unobservable regions? Theoretical frameworks exist in which physical constants vary across cosmic distances. Some inflationary models predict that different regions of the post-inflationary universe might end up with different values for fundamental constants, creating a patchwork of cosmic domains with varying physics. In such scenarios, our observable universe would represent one patch where constants happen to take the values we measure, while other patches beyond our horizon might have different gravitational strength, different particle masses, different electromagnetic coupling. We cannot rule out such possibilities through observation because observation cannot reach the relevant regions. If physical constants vary only on scales larger than our observable horizon, we would see perfect uniformity within our cosmic bubble, while living in a fundamentally heterogeneous universe. This scenario seems less parsimonious than universal uniformity, but parsimony is a methodological preference, not a law of nature. The universe is not obligated to be simple. Similar limitations apply to questions about cosmic topology. General relativity allows for various global topologies, different ways space might be connected on the largest scales. The universe might be simply connected, extending forever without repeating, or it might be multiply connected, wrapping around itself such that traveling far enough in certain directions returns you to your starting point. A multiply connected universe might be finite in volume while remaining unbounded, possessing no edges even though it contains limited total space. If the universe has non-trivial topology with a characteristic scale larger than our observable horizon, we cannot detect it. We would see what appears to be infinite space, extending in all directions when actually we inhabit a finite cosmos with complex connectivity. Searches for topological signatures in the cosmic microwave background have found no evidence for such structure, but this null result only establishes that the topology scale exceeds our observable size. It does not tell us what topology exists beyond our horizon. The scientific method encounters genuine difficulty at the edge of the observable universe. Science advances through hypothesis testing, proposing ideas and checking them against observations. But hypotheses about unobservable regions cannot be tested against observations by definition. Claims about the total universe beyond our horizon can be evaluated for internal consistency, for compatibility with observations within our horizon, and for theoretical elegance. But they cannot be confirmed or falsified through direct evidence. This does not make such claims meaningless or unscientific, but it does place them in a different epistemological category than claims about observable phenomena. Acknowledging these limits is not intellectual surrender. It represents honest recognition of the boundaries of empirical knowledge. Within the observable universe, science has achieved remarkable success in explaining cosmic structure, evolution, and dynamics. The models we have developed make precise predictions confirmed by precise observations. We understand immensely more about the cosmos than any previous generation of humans. This understanding gives us confidence in extrapolations beyond the observable edge, even while we acknowledge that such extrapolations cannot be verified. The edge of the observable universe marks where confident knowledge gives way to reasonable inference, where observation yields to theory, where science must admit the limits of its empirical foundations. This boundary is not a failure of scientific method, but a natural consequence of living in a cosmos with finite age and finite speed of information propagation. Understanding this boundary clearly, recognizing both what it allows us to infer and what it prevents us from knowing, represents essential intellectual honesty about our cosmic situation. What lies beyond the edge remains genuinely unknown in a way that differs from ordinary scientific uncertainty. We do not know what lies beyond. In the same way, we do not know whether a particular exoplanet hosts life. The latter ignorance is temporary, potentially resolvable through better observations or future exploration. The former ignorance is permanent, built into the structure of space-time, immune to technological progress. The edge of the observable universe is not a challenge to overcome, but a fundamental constraint to understand, shaping what questions about the cosmos admit empirical answers and what questions must remain forever open. Stand anywhere on Earth and look toward the horizon. That line where sky meets ground exists only from your perspective. Walk toward it and it recedes. Run toward it and it still recedes. The horizon is not a place. It is a relationship between your position and the geometry of the planet. The word itself comes from the Greek for boundary or limit, but the horizon limits only vision, not existence. Land and sea continue beyond that apparent edge, invisible but undeniably present, accessible to anyone willing to travel. The edge of the observable universe shares this fundamental character, while differing in crucial respects. Like Earth's horizon, the cosmic edge exists only relative to an observer's position. Like Earth's horizon, it recedes as you approach. Like Earth's horizon, it marks a limit of visibility rather than a limit of existence. But unlike Earth's horizon, the cosmic edge cannot be approached through travel. Unlike Earth's horizon, it constrains not merely current observation but all possible future observation. Unlike Earth's horizon, it separates not just seen from unseen but knowable from forever unknowable. The observable universe is a sphere of information centered on every observer in the cosmos. Light carries data about distant events across space at the cosmic speed limit. Where sufficient time has elapsed for that light to arrive, observation becomes possible. Where insufficient time has passed, observation remains impossible regardless of instrumental capability or technological advancement. The edge marks where time runs out for light, where the finite age of the universe catches up with the finite speed of information propagation. This edge is not a wall, not a barrier, not a surface you could touch or photograph or crash into. It is a temporal boundary projected onto spatial coordinates. The farthest things we can see are also the most ancient things we can see, not because distance correlates with age in some mysterious way, but because seeing far means seeing light that travelled long, which means seeing light that departed long ago. The edge of the observable universe is simultaneously the edge of observable time. Looking toward it means looking backward through cosmic history toward the universe's earliest moments. Every observation of a distant object is therefore an act of temporal archaeology. The photons entering your eyes or your telescope left their sources at specific moments in cosmic history. Nearby objects reveal their recent past. Distant objects reveal their ancient past. The most distant observable light, the cosmic microwave background, reveals the universe as it existed 380,000 years after the Big Bang, when atoms first formed and space became transparent. We see no farther, because before that moment, there was no light travelling freely to see. This temporal dimension of cosmic observation creates a profound asymmetry in what we can know. We possess extensive knowledge about the universe's past because light from that past reaches us constantly. We photograph galaxies as they appeared billions of years ago. We detect radiation from the cosmic infancy. We reconstruct conditions at even earlier epochs through indirect evidence and theoretical reasoning. The past of the cosmos lies open to investigation, limited only by the sensitivity of our instruments and the cleverness of our interpretive methods. The present of the cosmos remains largely hidden, We cannot see the universe as it currently exists because light from distant regions has not had time to arrive. The most distant galaxies we observe appear as they existed over 13 billion years ago. What those same galaxies look like today, whether they still exist in recognizable form, whether they have merged with neighbors, whether they continue forming stars or have gone dark, we cannot know. Light carrying information about their current state will not reach Earth for billions of years. By the time it arrives, that state will itself be ancient history. The future of the cosmos hides behind an even more impenetrable veil. We cannot observe events that have not yet occurred. We can predict the future through physical theory, extrapolating current conditions forward using known laws. But such predictions remain forever unverifiable for epochs beyond our own cosmic moment. The universe of the far future will differ dramatically from the universe we observe, yet we can never confirm our predictions through direct observation. This temporal structure of cosmic knowledge reaches its most extreme form at the observable edge. When we look toward the cosmic microwave background, we are looking at the universe's past in the most literal possible sense. The edge of the observable universe is the edge of observable time. Beyond it lies not mysterious space, but unobservable history. Epochs before the universe became transparent, moments too early for light to have reached us, even traveling since the beginning. The situation grows stranger when we consider that every point in space defines its own observable universe. An observer in a distant galaxy, billions of light years from Earth, would have their own cosmic horizon centered on their position. Their observable universe would overlap substantially with ours, sharing many visible galaxies and cosmic structures, but it would also extend into regions we can never see, while excluding regions visible to us. Neither perspective is privileged. Neither observer occupies a special position. Each simply sees the cosmos from their own vantage point, limited by their own temporal horizon. This multiplicity of observable universes underscores that the edge carries no cosmic significance beyond defining what particular observers can know. The universe does not care about our horizon. It does not organize itself around our position. The edge exists entirely as a feature of our relationship to the cosmos, not as a feature of the cosmos itself. Space continues beyond our horizon, just as it continues within it. Physics operates beyond our edge, just as it operates within our visible sphere. The boundary between observable and unobservable reflects the geometry of information propagation, nothing more. Yet this seemingly modest boundary has profound implications for the project of understanding reality. Science aspires to describe nature as it actually exists, independent of human perception and position. But the edge of the observable universe places fundamental limits on this aspiration. We can only verify claims about regions accessible to observation. Claims about unobservable regions can be evaluated for consistency, plausibility, and theoretical elegance, but they cannot be confirmed or falsified through empirical testing. The edge divides physics into two domains, the verifiable and the forever conjectural. The future of cosmic observation makes this division more stark rather than less. Dark energy accelerates the expansion of space, carrying distant regions away from us faster than light can travel. The cosmological event horizon marks the distance beyond which light emitted today will never reach Earth regardless of how long we wait. This horizon lies closer than the current observable edge, meaning some regions we can presently see have already passed beyond our future observational reach. Light they emit from now on will travel forever without arriving. The implications for future observers are dramatic. Over the next 100 billion to 2 trillion years, cosmic expansion will carry nearly all external galaxies beyond the event horizon of our local group. The Milky Way, Andromeda, and their gravitational companions will have merged into a single massive galaxy floating in apparently empty space. The cosmic microwave background radiation will have redshifted beyond detection. Distant galaxies will have vanished completely, their light stretched to infinite wavelength by eternal expansion. Astronomers living in that distant future, if any exist, will face a radically impoverished cosmic view. They will observe their local galaxy, perhaps accompanied by remnants of the original local group members. Beyond that, they will see nothing. No distant galaxies dotting the sky, no cosmic microwave background glowing faintly in microwave telescopes, no evidence of the rich cosmic structure we observe today. The expansion of the universe will have erased the observational foundations of modern cosmology. These future observers might develop sophisticated physics. They might understand gravity, electromagnetism, quantum mechanics, and nuclear forces as well as we do, or better. They might even develop theoretical frameworks suggesting that more galaxies should exist beyond their observation. But they will have no way to confirm such theories. The evidence we rely on to establish cosmic expansion, the redshift of distant galaxies, will not exist for them. The evidence we use to determine cosmic age, the cosmic microwave background, will not exist for them. They will live in an observational desert, cut off from the cosmic context that makes modern cosmology possible. This scenario reveals something important about our own cosmic moment. We happen to exist during an epoch when the observable universe remains rich with information. We can see billions of galaxies spanning billions of light years. We can detect the cosmic microwave background and decode its messages about the early universe. We can measure the expansion of space and infer the presence of dark energy. These observations are not eternally available to all possible observers. They are temporarily accessible to observers existing during a particular cosmic epoch, an epoch that will eventually end. The window of cosmic observability is closing, not rapidly in human terms, but inexorably in cosmic terms. Each passing moment sees additional galaxies cross beyond our event horizon. Each cosmic epoch reduces the fraction of the universe accessible to observation. We exist in what might be called the cosmic noon, an era after the universe became transparent but before expansion has isolated us completely. Earlier observers would have seen a smaller, denser cosmos. Later observers will see a sparser, emptier one. Our view is not the view, just a view, one perspective among the infinite possible perspectives distributed across cosmic time and space. This temporal contingency of observation raises questions about the nature of cosmic knowledge itself. Our theories describe a universe extending far beyond our observational reach. They posit billions of galaxies beyond our horizon, continuing through space in all directions without limit. They suggest physical laws operating identically throughout the cosmos, regardless of whether any observer can verify them in any particular region. These theories work extraordinarily well within the observable universe, but their extension beyond the observable edge remains permanently untestable. We face a choice about how to regard claims concerning unobservable regions. One approach treats such claims as meaningless because they cannot be empirically verified. This strict empiricist position refuses to speculate about what lies beyond observation, confining scientific discourse to the directly testable. Another approach treats such claims as meaningful but uncertain, legitimate extensions of verified theories into domains where verification remains impossible. This more permissive position allows scientific reasoning about the unobservable while acknowledging the distinctive epistemic status of such reasoning. Neither approach eliminates the fundamental limitation. The edge of the observable universe marks a boundary of knowledge, not merely a boundary of current knowledge that better instruments or longer waiting might overcome. Some information about the cosmos is permanently inaccessible to any observer at any position at any time. This is not technological limitation, but physical law. The finite speed of light, combined with the finite age of the universe and the accelerating expansion of space, creates barriers that no conceivable advancement could breach. The questions we can meaningfully ask about the cosmos are therefore constrained in ways that human intuition finds uncomfortable. We naturally want to know what exists beyond the edge. We want to know how far space extends. We want to know whether the universe is finite or infinite, whether it has boundaries or continues forever, whether our observable bubble represents a typical sample or an unusual fluctuation. These feel like factual questions with definite answers waiting to be discovered. But the edge of the observable universe suggests that some of these questions may lack empirically accessible answers. not because the questions are confused or meaningless, but because the information needed to answer them is physically unavailable. The universe might be infinite, extending forever in all directions, but we can never observe enough of it to establish infinitude. The universe might be finite, wrapping around on itself in some complex topology, but we can never see far enough to detect the wrapping. The question has an answer, but the answer lies beyond all possible observation. This situation differs fundamentally from ordinary scientific uncertainty. When we do not know whether a particular exoplanet hosts life, we can hope that future observations will resolve the question. When we do not know the mass of a certain particle to sufficient precision, we can build better experiments to measure it more accurately. Ordinary uncertainty yields to persistence and ingenuity. The uncertainty at the cosmic edge does not. It reflects the structure of space-time itself, immune to technological progress, permanent by the laws of physics. Recognizing this permanent uncertainty is not intellectual defeat but intellectual maturity. Science has always acknowledged limits on what can be known. Quantum mechanics revealed fundamental limits on simultaneous measurement of complementary properties. Thermodynamics revealed fundamental limits on energy extraction and information processing. General relativity revealed fundamental limits on signaling faster than light. The edge of the observable universe reveals fundamental limits on cosmological knowledge. Each of these limits reflects deep truths about reality, rather than superficial constraints on human capability. The edge of the observable universe also reveals something profound about the relationship between observation and reality. We tend to assume that reality exists independently of observation, that the universe would continue whether or not anyone observed it. This assumption seems obviously true, and probably is true, but the edge reminds us that observation is not a passive window onto reality. It is an active process embedded within reality, constrained by physical laws, limited by cosmic geometry. Every observation we make involves light or other signals traveling from source to detector. Every signal has a finite speed. Every detector occupies a specific location in space. The information available to any observer depends on their position, the age of the universe, and the history of expansion. There is no view from nowhere, no observation that escapes these constraints, no access to reality unmediated by the physics of information propagation. The observable universe is not the universe. It is our window into the universe, shaped by our position and the nature of light. The edge of that window is not the edge of reality, but the edge of our access to reality. Beyond the edge, the universe presumably continues, but we cannot see it, cannot study it, cannot confirm its existence through any direct means. We infer its presence from the smoothness of our own observable region, from the logic of physical theory, from the absence of any mechanism that would make our horizon special. But inference is not observation. Probability is not certainty. The edge divides what we know from what we merely believe. This division shapes the intellectual humility appropriate to cosmology. Within the observable universe, scientists can make strong claims backed by extensive evidence. The cosmos began in a hot, dense state, approximately 13.8 billion years ago. Space has been expanding ever since. Matter clumped into galaxies organized in a cosmic web of filaments and voids. Dark matter outweighs visible matter by a factor of roughly 5. Dark energy drives accelerating expansion. These claims rest on multiple independent lines of evidence, converging observations from different instruments and methods. Successful predictions confirmed by subsequent measurement. Beyond the observable edge, such confidence becomes inappropriate. Claims about the total universe must be held more loosely, acknowledged as theoretical extrapolations rather than observational facts. The cosmological principle might hold everywhere, making our observable region typical of the whole, or it might fail beyond our horizon in ways we cannot anticipate. Physical constants might remain unchanged throughout the cosmos, or they might vary in unobservable regions, creating domains with alien physics. The universe might extend infinitely, or it might end just beyond our horizon in some unforeseeable manner. We do not know which possibility is correct. We cannot know through any conceivable observation. This is not a temporary gap in knowledge awaiting future resolution, but a permanent feature of our epistemic situation. The edge of the observable universe marks the boundary where confident knowledge gives way to informed speculation, where science must acknowledge the limits of its empirical foundation. This boundary reveals something important about what science can and cannot tell us about existence. Science excels at describing regularities in nature, formulating laws that predict observations with remarkable accuracy, explaining phenomena through mechanisms that can be tested and refined. Within the observable universe, science has achieved extraordinary success in meeting these goals, but science operates through observation and experiment. Where observation becomes impossible, science loses its empirical grounding and must proceed more cautiously. The questions that haunt human consciousness, the questions about ultimate reality, about the totality of existence, about what lies beyond all possible experience, these questions press against the cosmic edge. We want to know if we are alone in the universe, but we can only search within the observable volume. We want to know if the cosmos is finite or infinite, but we can only measure within our cosmic horizon. We want to know if other observers exist beyond our reach, constructing their own cosmologies from their own limited perspectives, but we can never detect them if they lie beyond our event horizon. The edge of the observable universe frames these questions without answering them. It establishes the arena within which empirical investigation can operate. It marks where investigation must yield to speculation, where knowledge must acknowledge its boundaries, where honest inquiry must confess uncertainty. This framing is itself a kind of knowledge, a meta-knowledge about what can be known. Looking out at the night sky, we see not just stars and galaxies, but the history of the cosmos spread across space. The nearest stars show us the recent past, light that left just years ago. More distant stars reveal earlier eras, light from decades or centuries past. The Andromeda galaxy shows us conditions 2.5 million years ago. The farthest visible galaxies show us conditions over 13 billion years ago, and the cosmic microwave background shows us the universe as it was when atoms first formed, nearly 14 billion years in the past. This cosmic time machine works in only one direction. We see the past, but not the present. We see the young universe, but not the current universe. The light reaching us tonight departed its sources at specific moments in history and has been travelling ever since. Each photon carries a timestamp indicating when it began its journey. Collect enough photons, and you can reconstruct a history of the cosmos, piecing together how galaxies formed and evolved, how cosmic structure developed, how the universe transformed from a hot plasma into the cold, dark, vastly structured space we observe today. The edge of the observable universe marks the end of this historical record. Beyond it, no photons have arrived. The history encoded in those undelivered signals remains unread, a cosmic archive forever inaccessible. The earliest chapters of cosmic history, the moments before recombination when the universe was opaque, lie beyond the electromagnetic edge. Even earlier chapters, the inflationary epoch, the possible genesis of spacetime itself, lie beyond the reach of any observation yet conceived. But within the observable volume, the universe offers itself to investigation with remarkable generosity. 2 trillion galaxies fill the visible cosmos. Hundreds of billions of stars populate each galaxy. Countless planets orbit those stars. The cosmic microwave background encodes conditions from the earliest observable epoch with exquisite precision. Gravitational waves ripple through spacetime, carrying information about cataclysmic events. Neutrinos stream through space, bearing witness to nuclear processes in stellar cores. The observable universe teems with information waiting to be gathered, analyzed, and understood. The edge that constrains our vision also defines the richness within it. Precisely because we cannot see beyond the cosmic horizon, everything we can see carries significance. The observable universe is not an arbitrary sample of infinite space, but a defined domain with identifiable boundaries. Within this domain, we can attempt complete inventories, statistical surveys, comprehensive maps. We can aspire to full understanding in ways that infinite space would preclude. The edge of the observable universe is not a wall hiding secrets. It is not a barrier concealing wonders. It is not a surface marking where reality ends. It is a horizon of information, a boundary where the finite age of the cosmos catches up with the finite speed of light, where time itself becomes the limit on observation. Beyond it, space presumably continues. Galaxies presumably populate the void. Physics presumably operates as it does within our horizon. But we cannot confirm these presumptions. We cannot observe what lies beyond. We can only infer, extrapolate, and wonder. This wondering is itself significant. Humans evolved on one small planet, orbiting one ordinary star in one typical galaxy. Nothing in our evolutionary history prepared us to contemplate cosmic scales. Yet here we stand, measuring the age of the universe, mapping the distribution of galaxies, detecting the afterglow of the Big Bang itself. We have learned to see far beyond our immediate environment, to comprehend structures larger than our ancestors could have imagined, to ask questions about the totality of existence. The edge of the observable universe marks where these questions encounter fundamental limits, not limits of imagination or effort or technology, but limits built into the fabric of reality. Understanding these limits does not diminish the achievement of cosmic knowledge. It contextualizes that knowledge within the physical constraints that make observation possible at all. We see what light can reveal. We know what signals can convey. Beyond the reach of light and signals, knowledge yields to inference, and inference yields to silence. The observable universe is our window into cosmic reality, shaped by our position in space and time, bounded by the physics of information propagation. The edge of that window recedes into the past as we look toward it, revealing ever earlier epochs of cosmic history. Beyond the edge, reality presumably continues, but observation cannot follow. We are finite beings in a possibly infinite cosmos, seeing far but not far enough, knowing much but not everything, asking questions whose answers may lie forever beyond our grasp. This is the human situation at the cosmic edge. Informed but limited, curious but constrained, reaching toward totality while embedded in particularity. The edge of the observable universe is not the edge of existence. It is the edge of knowledge, the horizon where understanding meets its boundaries and must acknowledge them with honesty. The universe continues beyond that horizon, but we have reached the limit of what light can tell us, the limit of what observation can reveal, the limit of what questions can be answered through empirical means. The rest is silence, not empty silence, but the silence of a cosmos too vast, too ancient, and too swiftly receding to ever fully reveal itself to observers bound by the speed of light and the age of time.